today's webinar is going to be on the topic of summer comfort, and of course, how we relate this with buildings and how to build better, considering summer comfort. So today I will host this webinar. I'm working at the United Nations Environment Program in a group called Coalition. We have different initiatives for sustainable cooling, including this part that's regarding buildings as well. And today I will present a little bit on the thematics, and after show work that we are developing inside the Coalition. That's the Passive Cooling Working Group. After that, we are going to have 3 very interesting presentations from our distinguished presenters. So the first one will be on the House of Sustainable Development of Morocco. And this will be presented by Soufiane Lomari. And the second one is senior house that's called Mirador de Gracia in Spain from Oliver Style. And the third one is a deep retrofit that was made in France in a house where they think about summer comfort in the attic. And Aymeric Peronnau-Nyssens is going to present for us. So I start soon about the introduction. So the question today, and everybody can feel it, especially those that are placed in Europe, we are having a lot and much more frequent heat waves. The general temperature, the mean temperature are rising, but also the extreme events are much more frequent. And this is getting the concern of most world population. And in addition to this point, we have the majority of the population that's located in cities. So that's a big concern because cities, they have an effect that we call urban heat island phenomena that's related to higher temperatures than the countrysides beside the cities. And why it happens? Because we have different materials, different colors on the surfaces, as well the shapes, that everything in cities, they are tending to trap the heat. And in addition to that, we have all the human activities. So it means that besides the global rise of temperatures, we have the population living in cities suffering even more. So the situation is even more critical in some cases. And then a fast and, let's say, easy solution for that, we could say, and most of people without a further thought would think about AC, so air conditioning. But the problem of air conditioning, it's not magical. It takes the heat from inside and it puts outside. So it means outsides get hotter. And in addition to that, it uses a lot of electricity. So more electricity use, more emissions associated, and then we have also the increasing in global temperatures. So that's the cooling challenge we can see nowadays. Cooling is already 10% of the global electricity use. That's a huge impact. And people are starting to see the importance of working on this and thinking even in not just in mainly hot climates, but even in colder climates. We also see people taking more care about summer comfort. And then we have already more than 3 billion cooling appliances today, and they are going to be much more in the next decades. So we need to act in order to, from one side, slow down the emissions related to cooling so that we don't have this vicious cycle acting. And on the other side, to think about how we provide thermal comfort and protect the population, right? So we have both mitigation and resilience together in this challenge, in this cooling challenge. So we think about this, we can talk about the sustainable cooling hierarchy. As I already told, AC is not always the best solution, although it can seem the easy one. So the idea is to go step by step and start with how to make buildings more efficient, thermally efficient for summer, so that you don't need to use electrical appliances and equipments. And this is related to building design, and I will talk about this later. And also after that, you can start to think about using technology, yes, that use electricity, but low energy cooling. For example, install fans on the ceilings as well. This provides a lot more comfort than we can imagine, and thinking about new ways of understanding comfort is very important as well to take in consideration these solutions. And after that, of course, we can always go through the air conditioning. And then if we want something with less impact, then you need to have energy efficient equipment, and also try to phase down the HFC with high global warming impacts. So in this aspect, today I'll talk a little bit more on focus on the buildings, because this is organized by Construction 2021, and to have this idea on what we can do to better design buildings. So the idea of passive cooling. So passive cooling is basically using nature in our favor instead of against us. And then thinking how to avoid heat to go inside the building and how to evacuate the heat that's already in the building. So we can use different sources in nature. For example, to evacuate the heat, we can use wind. And to avoid the heat entrance, we need to think about how to block the solar gains. And also we can think about the envelope of the building. So the different materials, colors we use in this envelope is going to change how these buildings is responding to the thermal environment and interacting with it. And even like the shape of the building as well can be favorizing some of the strategies we can have. And of course, using nature, that's for free. It's not costing electricity at least. And then this can help us to have cooling as well. So I'll go very fast up through these different styles of passive cooling. So the first, natural ventilation. So the idea when you design a building would be to have windows that are opening different directions of the building, so you can have airflow passing by. And then now you can also think about the stack ventilation, because the hot air, it goes up because of density, lower density. So if you put and place openings on the higher part of the buildings, it can help to have a natural air movement. And of course, night ventilation as well. That means if you have lower temperatures by night, you can use this, or maybe you close all the windows during the day and avoid the heat to go inside. And during the night, you can open and have naturally more thermal comfort building. And when we think about shading, you need always to think how to avoid the solar gains. Then you can have roof overhangs, brise soleil, or even vegetation can be good for this. And then you can always think also about how to orient your building and do the shape in order to minimize solar exposure and to enhance the ventilation. So thinner buildings, you can have better ventilation. If you orient the windows in the direction of the main wind directions, it can also help to harness this potential. You can think about putting the longer facades for the direct directions that have less solar exposures. So it's a lot of thinking, and that's related to microclimate and the climate of the place you are constructing the building. So regarding the envelope, it's important always to think also about the colors and the reflective properties of the facade and also the floor, mainly the floor as well, so that you can avoid to absorb so much solar energy. So use lighter colors for the surfaces, and you're going to reflect to the atmosphere the part of the solar radiation. Insulation is also a strategy that's important, especially when you think about buildings that have air conditioning. So they need to have a bit of insulation between the inside and outside, so at least it's going to be more efficient, as we having buildings that are constructed for winter as well. And regarding thermal mass, then it depends on where you're constructing. But if you have a higher thermal mass, you can do a balance of the temperatures during the day, and the heat gets stored into the walls and the envelope, and by night it can be released when it's fresher. Or in places that you don't have a lot of thermal differences between night and day, maybe lower thermal mass is better, so then you can use more ventilation all through the days. And then always, we can also think about solutions that are related to nature, because trees, nature in general, you have the evapotranspiration. So a lot of heat is released in this process of evapotranspiration, and of course the shade that they provide. So this can be used in conjunction of the buildings, around the buildings, on top on the facades as well. So the idea here is to have like a different strategies that you can keep in mind and how you can put them together, because just one maybe is not enough to face the extreme temperatures we are having in summer. So then you need to combine the different strategies and specifically study this for the local microclimate, because the one thing that's going to work in Cambodia is the problem not going to work in France, because you have different humidity, you have different temperatures, the temperature variations. So this is very important. Also, what are the wind directions? Everything needs to be thought locally. So that's very interesting to share the experiences from people in the same climate. So then you can have a knowledge on what are the best strategies. So regarding this passive cooling, we have in the UNEP, together with the Coalition and Global ABC, we have the passive cooling working group that's trying to put together different actors to accelerate the adoption of passive cooling strategies, especially when we are talking about the developing countries that might have less investment to this. So it's a very important source as well. So the idea is to have knowledge sharing, capacity building, and policy support. And our group, working group, is developing webinars as well. We have different webinars that have been presented. The first one there, climate responsive design, is going to be in 15 weeks. So if anyone is interested, don't hesitate to contact me so I can share also the information. And in this working group, we also share the knowledge. As I told you, it's important to have know what are the best practices in each place. So we have this different projects that were finalized by partners. They share about the financial costs, which strategies they use for passive, for AC, for systems, and what are the performance. So it's very interesting to go through them. And we are nowadays developing the passive cooling guidelines. That's going to be a big document providing some ideas on what are the best strategies, what are the existing strategies, and what's the physics behind this, and how we can adapt this to building codes in different countries. So it's very interesting work we are developing. It's going to be released probably at the end of this year. So we have different co-chairs from the UNEP. So Genai, myself, and also represents from academia as Professor Lorenzo and Professor Rajan, and also from the business part, Hub Kaiser. So if you are interested in joining this working group, please send me an email just to say I want to join the group so I can share the webinars and also the activities. So thank you very much. We are going now for the presentations of the study cases. And the first one is Soufiane Lomari. That's an engineer in energy and also environment. And he's going to show the case of a sustainable development house. And Soufiane, can you take the... Yes, perfect, thank you.
Thank you. Today I will be presenting you with the case study for the houses of sustainable development. To give you a bit of context about the project, the House of Sustainable Development is a building in Tangier, and it's in Morocco. It's an innovative educational space that the mission behind is to strengthen the population's human capital through awareness, education, and training on sustainable development. The core mission of the building is structured around three main axes: awareness and education on sustainable development, capacity building for local and nonprofit stakeholders, and innovation and green entrepreneurship. And so it was basically laid, the first cornerstone was laid in 2016. It's a building with a surface, so with an area of 1,458 meters squares over 2 levels on a 4,600 landscape that contains sites that in the site contains gardens, ponds, and botanical trails. The building is an energy positive building. Mainly we have photovoltaic and micro wind production in the building, and the building produces 3 times its energy consumption, which allows us to avoid 27 tons of carbon dioxide per year. And on the subject that is more relative to this presentation, the building is designed to reach summer comfort without active cooling in the main spaces. And it accomplishes that mainly through three main axes. The first axis we will be talking about is its bioclimatic design. First of all, the passive strategies do most of the heavy lifting. So first of all, we oriented it so to limit the external approach. So solar projections first. As you can see in the first picture, the perforated Musharabis screen shade manages to limit the external gains through windows while also maintaining lighting comfort inside the building. A high performance envelope, mainly timber frame and masonry walls, with an U of 0.25 and then a roof of 0.20. And just for information, the code maximum in Morocco is 0.6. So we are much more performing than the regulations requires in Morocco. Another axis that is used inside the building is inertia and night ventilation. Basically, this is one of the main strategies that allows us to reach the comfort inside the building, is that the building is able to store coolness at night and release it during the day, which allows us to maintain a much more comfortable temperatures inside our rooms. And finally, we have daylight and greenery. The building is designed to achieve a maximum daylight factor inside most of the locals. And also we have a vegetation and a pond that with the objective of tempering the microclimate. And so we achieve a minus 73% in comparison to a Moroccan regulation baseline. And another very important aspect, one which we will mainly talk about in this presentation, is the earth-air heat exchanger. In fact, the building is equipped with an earth-air heat exchanger, also known as a Canadian well, that allows us to ventilate the rooms inside the building using fresh air and green free energy that we will basically get through the ground. In fact, using a fresh air intake that is located outside of the building, we have pipes that circulate in the ground, allowing this air to be refreshed during the summer and heated during the winter before it is injected inside the room, achieving comfort as well as clean air. So it is a pipe of 50 meters that goes under the ground, buried with a 3% 3-degree slope, and allows us to inject 500 meters square per hour inside each room. What we have done to actually measure the impact of this design is that we have run a simulation that we calibrated later via measurements. And the results that we have basically indicate, for example, that while we have a 28 degrees Celsius outside, the air on the inlet is 28 degrees Celsius, and after passing through our pipes, it is injected with a temperature of 22.4 degrees Celsius during summer, allowing us to gain around 6 degrees Celsius. And during the winter, we can drag air from the outside to 7 degrees Celsius and inject it with a 14.3, allowing us to gain 3 degrees for each volume of air. And we also evaluated the comfort inside the main buildings, and we achieved very high rates of comfort. And basically, in the biggest room, the hall of the building, we managed to keep it under 31 degrees Celsius, while we have 34 degrees Celsius on the outside, using absolutely no mechanical air conditioning. Well, what we would tell anyone building a similar building and how they can reconstruct our design, basically, the first idea is passive first. While the air heat exchanger is a finisher and it's a good thing to have, it is not the engine. Shading and inertia remove most of the load and they do most of the heavy lifting. It trims the last points of discomfort, and then we can add the the air heat exchanger to optimize the design. Another idea is that we should instrument from day one. To optimize the design, instrumentation is extremely important, mainly measuring outside temperature, the temperature that we inject, the air volume we inject, as well as the humidity. And then the final idea is that maintenance should be light within such system, but it is vital. Intake grates, filters, condensate siphon, a blocked intake kills performance silently, and so it is optimal that it is extremely important that the system should be well maintained. And basically, it is a system that is reproducible almost anywhere hot, since the temperature of the soil doesn't depend as much about the air temperature, and so the system can be reproduced anywhere on the Mediterranean on semi-arid climate. Hot days, cooler nights provide most of the heavy lifting. And another extremely important point about our system is that it is extremely low tech. The standard HDPE pipe and basically fans are the main parts of the system that is used. No refrigerants, and also negligible energy running since we don't have active air conditioning. And it pairs naturally with night ventilation and solar shading. However, in some humid climates, condensation needs to be managed since it could introduce some mold risk. And that is all for this part of the presentation. Do you have any questions?
So our question is, hello, what about radon in the soil?
Well, in the part that we have installed our pipes, because basically our building is a small, how can I explain this? Our actual building represents a small part of our landscape. And on this landscape, we have mainly gardens, ponds, and botanical trails. So while there have been studies to eliminate any risks, we don't actually have any radon on sites.
Okay, thank you very much. Thank you so much for the presentation. Very interesting project, Soufiane. And I think Alexandra was happy with the answer. So she's thanking you in the chat. So we are going to our next presentation. So Oliver Style, that's an architect and CEO of Praxis Resilient Buildings. And so you present the Mirador de Gracia. Yeah, please.
Thank you, Lorena. That's very kind. I can't claim to be an architect. In fact, I am an energy consultant, and I work in HVAC engineering and building envelope design and passive house certification. But anyway, thank you. Great to be here, and thank you for Soufiane for your presentation. That was really interesting, and Lorena too. So you've both identified quite a few kind of key design strategies that are going to help us keep buildings cool. Excuse the pun, but of course this is a really hot topic. You know, we are being hit by heat waves in Europe again and again recently. On a global level, I think there's going to be almost 2 billion more people buying air conditioning units for their houses from here till 2050. So we really need to look at this, and I think that of the presentations that that have come so far, I think the key takeaways is we need to look at the thermal envelopes and demand reduction before looking at air conditioning, if possible. You know, that's really fundamental. So I just want to share a few things with how we did it in this project, Mirador de Gracia, which is an elderly people's residency and nursing home in Barcelona. Just very briefly, some information about my company, what we offer. These are our services. We do a lot of work looking at overheating mitigation in warm climates, warm humid climates, warm dry climates, for new build and retrofit, air tightness testing, HVAC design, and building physics. So at a general level, where are we heading? In terms of demographics, we've got a world population that's aging, as we know. That's going to be by 2050 more than double the number of people over 60 years and older. So nursing homes, elderly people's residencies, all of these services and infrastructure is going to be more necessary than ever. And of course, this is a collective that are particularly vulnerable to heat waves. We're working with a client who's developing and building 7 nursing homes, all to Passivhaus standard. Of course, the fact that there's an aging population means that there's an increasing market. Care homes are very power-hungry buildings. If the developer's also the owner, they have a vested interest in making the building energy efficient, free from moisture damage, and comfortable. And again, as I said, elderly people are a vulnerable collective in terms of thermal comfort. So heat waves is really key here, to create spaces where elderly people can be safe and comfortable in these hot spells. I think there was quite a shocking figure that there was more people that died in the 2003 heat wave, I think it was in France, than people who died in COVID. So this is really literally a life or death thing. We also know that the energy prices are spiking every time there's a geopolitical conflict. That's the case. When these heat waves kick in, obviously the electricity grids suffer a major stress because everybody turns on their air conditioning units. So that's another kind of backdrop here. Just very briefly, the client of this project is developing, as I mentioned, 7 different nursing homes, all in warm climates in Catalonia, the northeast of Spain, and Valencia, the Mediterranean coastal areas. Here you can see the project that I'm going to present briefly here is Mirador de Gracia. It's up in the Collserola Hills, just above Barcelona. Warm, humid in the summer. A short winter, but a winter nonetheless. And I think, in my experience, these warm, humid climates near the sea are some of the most tricky ones to deal with overheating. Not because the temperatures, peak temperatures are very high. The sea modulates those peak temperatures, but the problem a lot of the time is the humidity and the minimum temperatures in the night. Things don't cool off, and that's really much worse in heat waves, because in the nighttime, unless you have air conditioning on, you can't sleep, and that creates a lot of problems. Brief summary of the building here. We're talking about just about 5,000 square meters of floor area, 8 floors, there's about 75 rooms, 143 people here, maximum capacity. The nursing home has an industrial kitchen, gym, pharmacy, laundry, hairdresser, 7 common rooms, and 2 roof gardens. So it's a building that's packed with services, a lot of people, heat, and so on. So fortunately, with the slide transitions, I've lost a few of the photos here, but here you can just see some of the construction as it went up. Okay, what we can see is there's quite a lot of earth movement that was needed to get the building up. That means we had quite a lot of the building to ground, and we used that as ground coupling. So that was one of the strategies we've used to help keep the building cool. Ground coupling is reducing the thermal insulation of any building element that's in contact with the ground so that you can dissipate heat towards it. You can also see here that the reinforced concrete floor slabs and columns for the structure of the building also gave us quite a lot of thermal mass. And here in this photo, you can see, looking down to the sea in Barcelona, just about that every window has an external blind with Venetian blinds that can be angled at specific angles to allow for some natural light, but keep direct solar gain, so the sun coming in. So that's fundamental. And of course, you can also see the white color, so cool colors. What you've both mentioned in the previous presentation is really important to keep the transmission heat gains as low as possible as they come in. So there's a lot of challenges for getting nursing homes up and running, comfortable and efficient in warm climates. I think sun performance is obviously one of the key things, and that's the subject of this presentation. There's various other things that are challenging: large, very efficient air handling units, commercial kitchens obviously are an issue to make them as efficient as possible, fire doors, laundry equipment, air tightness, low embodied carbon materials. I don't want to dwell too much on this because there's not so much the focus of the webinar. One of the strategies we looked at, unfortunately this slide has been kind of taken apart a bit, but we looked at glazing specification by facade comparing thermodynamic simulations and daylighting simulations, which balanced heating consumption, cooling consumption, and natural daylight. So what we did through those simulations was to determine that some facades needed to have low emissivity glazing and others needed low emissivity and solar control glazing. So we varied the specification of the glazing per facade to help with summer overheating. On the active side, we have air-to-water heat pumps and a chiller, which provide significant cooling power. So these are obviously active systems. They are designed in cascade so that one can be turned on, or two, or three. But that means we can run the active cooling system at the lowest possible power. One of the key things, as I mentioned, was external shading devices. As you can see in the image there, Venetian blinds. The slat angle can be controlled through the BMS system. So that's one of the first and most important things in any warm climate. Keep the sun out. The solar control glazing, as I mentioned, was put in place in the facades with more radiation. We had cool colors on the outside, so we have an external thermal insulation system rendered in a light color. As far as possible, we also tried to keep equipment gains down by locating HVAC and hot water plant outside of the thermal envelope, so we kept that heat outside. And then one issue which is fundamental in all residential buildings, at least, as well as hotels and so on, is hot water recirculation circuits. So this is the pipes which are taking hot water around the building so that people can use it for showers and stuff. In the summer, that can be a real killer because you've got water going around the building at 60 degrees. And of course, that can heat up, particularly the circulation areas, the common areas, and that can be a real problem for overheating. So what we did in this project was to control the recirculation of that hot water via the return temperature, modulating the pump flow rate so that recirculation was kept to a minimum. Fundamental as well, I think, in any larger building is to use dynamic simulation to assess some performance and overheating. So we looked at specific rooms in the building through the simulations. We identified rooms with the highest required peak cooling powers. We modeled those rooms to make sure that we had enough active cooling, but also to test the effectiveness of all of the passive design strategies that I mentioned, external blinds, cool colors, and so on. One thing to mention in nursing homes is the natural night ventilation with thermal inertia is not possible in this project for two reasons. One, elderly people with dementia cannot have access to open windows. And so, in fact, for security reasons, there's no handles on the window, so people can't open the windows. That takes natural ventilation out of the picture. The other thing to bear in mind is that natural ventilation with thermal inertia is only going to be effective in climates in which the nighttime temperature is below 18 degrees roughly. Okay, in these warm climates in the summer, you never really get very low nighttime temperatures, so you're not going to be able to draw too much heat out of the building. Anyway, here we are, the conclusions. So warm climates need specific strategies to reduce internal heat gains and deal with overheating. And of course, I think in a sense of elderly people's homes, that's fundamental as we move forwards, because a growing elderly population and increasing heat waves means we really need to look at that. So final conclusion is don't take life so seriously. It's not like you're going to get out of this one alive. So thank you very much. And if you've got any questions, I'd be very happy to answer them now.
Thank you very much for the presentation, Oliver. And yeah, it's very interesting to see integrated solutions for one building, and specifically thinking about the needs of this building. So please, all the participants, if you want to ask any questions, please add to the chat or to the Q&A. I have one question from my side, if you allow me. So I was thinking about how to convince the building owners to invest in passive house certification, when you consider that this also would include some costs to the construction.
Absolutely, that's a great question. I mean, I'll just give you one example. I was just recently in the US, in the United States, in a hotel which had been retrofitted to passive house standard, and the owner was also the architect and also the developer, interestingly. And he said that the real driver behind going to high performance building like Passive House was purely economical. By going to Passive House standard, they increased the asset value of the building by over $2 million, and reduced energy use by $250,000 a year. So I think the economic rationale is probably one of the strongest ones in that sense. You know, it's a good business case. The often arguments are made that Passive House increases cost. It doesn't. Shouldn't increase capital costs significantly. In this Mirador de Gracia project, there was a 4% uplift to reach Passive House standard. It was, which is not really significant, and energy savings of up to 85% in terms of running costs. So I think that is the key. I think that's the key issue to look at is basically the business case.
Okay, I understand. So basically you have some costs increasing, but also you can convince people to buy this by a higher price because they are going to be saving the whole life cycle of the building. Very interesting.
Sure, yeah.
Okay, thank you very much. Any other questions? Okay, so we are going to the next presentation. So Aymeric Peronnau-Nyssens is going to present the Living Attic. That was a project developed in France with a deep retrofit, and where they have they highlighted the importance of thermal comfort in the attic. So please, Aymeric.
Exactly. Thanks, Lorena. Hi everyone, my name is Aymeric Peronnau. I work for Velux. For those who don't know, Velux is a big roof window company that sells mostly in Europe, but actually worldwide as well. And I'm an energy and environmental engineer, and here to talk about Living Attic. A few pictures. This project, I'm going to get into the details very quickly, but the idea is for us to have a real example of good deep renovation with attic conversion that is comfortable in summer, but also energy efficient and also comfortable in terms of daylight, in terms of air quality, and many other things. Before I talk about the project in itself, let me introduce you to the project of the family, because this house was inhabited before the renovation, during the renovation, and it's still inhabited now after the renovation. And it's very interesting to talk about the project of the family, because at the end of the day, they decided to do this project. So they are a family of 4, 2 adults, 2 children. They lived in a house near Paris that was originally that was getting a bit too small for them, for this family of 4. They first wanted to move to another house, bigger house, but they struggled to find anything good, and they liked their town, and their friends were living nearby. The school of where the children was nearby. Everything was nearby. They didn't want to move out. They wanted to stay in their community. So they made the very good decision to renovate their house for energy efficiency and comfort, and to convert their attic to add a room that is going to be mostly dedicated to a home office, but not only. And us as Velux, we wanted to find a real project to showcase what we want to prove with attic conversion. So we worked with them to improve their initial renovation and attic conversion project. And in exchange, they let us use their house for monitoring, for testimonies, and for organizing visits. Basically to show the project and give some information about it. Their house is very typical of French houses. It's representative of 1/3 of French houses, suburban houses, and it's also a scalable project because in France we have now a housing crisis, and we have a big potential of creating square meters by converting attics. We have around 6 million attic that could be converted to create square meters. So this project is an example of that. But of course, I'm not going to spend too much time on this because I think we all know, and this topic has been addressed. We talked about the topic already quite a lot today. But our homes are not ready for heat waves at all, especially our attics when they are not properly renovated because they are more exposed to the sun. So we wanted to have a project where we have an attic conversion that's still comfortable in summer, even during heat waves, even without AC. There's no AC in the house. So as comfortable as possible using passive solutions without AC. We worked with an engineering office called Artelia, who did the design simulations and design process, but basically the design process is very simple. The first thing is you want to limit the temperature increase. So you want to insulate your walls and your roof. You want to protect, of course, the glazed surfaces. So in our case, in the attic, it's going to be the roof windows, but the whole house has been renovated as well. The second thing is you want to add thermal mass to delay the temperature peak and also flatten it a bit to have a lower peak temperature inside. And also when the temperature peak is delayed, you can remove the heat by ventilative cooling, mostly using stack effect or cross ventilation for a better, for a more efficient cooling. And in practice, a few pictures of before and after. In practice, what was done here? So in the attic, we insulated outside the roof, and also we added a layer of insulation inside. The Velux roof windows were automated for abundant daylight and ventilative cooling. They were, of course, protected with sunscreening, both blackout sunscreen and filtering light sunscreening, because as I said, it's a space that's mostly dedicated to working. So you want to be able to have some daylight even when the sunscreening is down. It seems like a detail, but it's very important for the quality of life in the house. For thermal mass, we added a heavy material under the sloped roof because, of course, roofs like that, they are built in wood. They have no inertia, basically. So you want to add it, and the only way to add it is to add heavy material under the slope roof in contact with the indoor air. And also that's a bit more futuristic, let's say, but still very replicable, there is a sliding window that is automated at the ground floor. So automated for opening at the same time as the roof windows, mostly in the morning, because for the living room window, mostly in the morning to avoid intrusions. But that allows us to have some stack effect in addition with the cross ventilation that's already going on in the attic. And also, I'm not going to go into the details, but the rest of the house was also renovated, as I said, also for energy efficiency, and not only, of course, for summer thermal comfort. In terms of results for thermal comfort, we measured last summer, and also we are measuring right now, but these figures are from last summer in France. We took 4 consecutive days where the outdoor temperature peaks were around 35 degrees. And during these days, the attic temperature was on average 8 degrees cooler than outside at the warmest time of the day, when it was at the warmest outside. We reached 3.5 degrees temperature decrease at night thanks to ventilative cooling. And also for those who are a bit more expert, let's say, we reached the second best category of the adaptive thermal comfort standard in the attic at the warmest time of the monitoring period. And of course, in terms of energy efficiency, we went from class F of the French EPC to class A, and we improved the energy performance by 66%. And we gained of course, we gained 35 square meter in the attic by converting it. So many good results on different aspects. But yeah, the approach to this renovation was more holistic than just improving thermal comfort and energy efficiency. It was we also looked into improving the daylight availability. So we still installed quite I was not say a huge glazed area in the attic because that's not clever, but we did not, let's say, sacrifice daylight and visual comfort for overheating. We still managed to find a balance. And also we tried to keep the carbon footprint of the material used as low as possible, but we still wanted to have a more like replicable project, so we could not go for the best in every category, but still we took it into account. Sorry. And to finish, I want to give the word to, kind of to the owners, because at the end of the day, they live in the house, and we can have all the figures we want if they are not satisfied, and the job is not good. In this case, it seems that they are quite satisfied, both with the thermal comfort, the light availability, and also the way they now live in their attic. The way the attic has transformed the way they live in their house, because now they spend more time in the attic together, as opposed to before, where they were all in their own bedrooms and more separated. Now they are more gathered and having good times together under the daylight. Thanks. Any question? I went a bit fast, but I hope you understood.
Thank you very much for the presentation, Aymeric. It's very interesting to see this holistic approach, thinking about thermal comfort, but the whole comfort as well, daylight, and also thinking about the embodied carbon. So we have a question from Marcus. Hi, Edon. What material was used to increase the thermal inertia in the attic? I had exactly the same question. Thank you so much.
We used, how do you say in English? It's can I give the brand of the material? Yeah, that's right.
Yeah.
Yes.
Or maybe saying French as well.
Yeah. Fermacell is more heavy. It's not plasterboard. I think it's gypsum fiber. I don't know exactly what it is, but it's plasterboard that's denser and heavier than the typical plasterboard, and we use 2 layers of it to really add some thermal mass as much as possible in an attic that was, of course, that had basically no thermal mass before that. Other questions?
Yeah, there's a question from Tatiana Delgado.
Yeah.
So what about the cost? Is it affordable for families, and could this approach be replicated on larger scale?
So the cost is around 200,000 euros. 50,000 of this was covered by public subsidies back when public subsidies were a bit more generous. Now it's getting scarcer and scarcer. And 50,000 were covered by a 0 interest rate loan, bank loan. It is quite a cost. I would not say it's replicable for everyone. That being said, now it's not the case anymore, unfortunately, but the government in France was giving quite some generous subsidies before that could help people to achieve like very ambitious renovations. In this one, we really wanted to have the best in everything. No, we still try to find a good balance, but we still, in terms of the performance, we try to really optimize. But yeah, it's a cost. It's not like a completely unrealistic project, but it's a cost, of course. But honestly, the family is really happy about the results. It really improved their everyday life, their energy performance, and that's unfortunately that's the if you really want to have a very efficient renovation, you need to it's still a bit expensive. but the passive solutions that are sunscreening, cooling, ventilative cooling, these are, I would say, cheap solutions that if you apply them to your house, you are already going to improve the indoor thermal comfort quite a lot without like crazy costs. And we also advocate for subsidies for families to install shutters in France, because many people still don't have shutters in France, which is a bit crazy, and considering how efficient they are to prevent overheating.
Thanks so much for the answers, Aymeric, and for the insightful presentation. So we still have some time. If anyone wants to ask other questions for all the presenters, you can add to the chat. And I have one question to the three of you. That's across this project that you worked. Is there one solution you would call most replicable, regardless of context? So which of the solutions do you find that's the easiest to adapt to other contexts? So if you can answer this.
I would say sunscreening.
Sunscreening
is always going to be efficient, and it will be, you can use it in any context. The challenges are maybe more a bit about like the aesthetic, how to integrate it, for example, on a heritage building. Sometimes we have heritage protection in France, for example, and like the shutters, you have to find the right one so it does not change the look of the facade too much, for example. But I would say that's the most replicable solution.
Thank you so much. Oliver, would you like to add some insights from your experience?
Yes, I mean, I agree with Aymeric. That's I think the key thing is external shading devices. You know, fixed, mobile, depending on orientation. I mean, I think that's a fundamental thing. Keep the sun out. I would also say that a step before that, if possible, and this applies more to new buildings, I think the architectural bioclimatic design is also fundamental. Buildings that are designed with large amounts of glazing to the west, for example, are always going to have overheating problems. It doesn't matter how much you shade them. It doesn't matter how much mass you put in there. It doesn't matter how many earth tubes, you know. The architectural design is really fundamental. So climate responsive design, architecturally speaking, is also, I think, the sort of departure point for all of this.
Perfect. Thank you so much for your insights. I would like to thank you, the presence of everybody here. The presentations were very interesting, and it's amazing to see integrated passive design and real cases, not just the theory, because in theory we know what could work, but then we see in reality, we can see the costs of this, the challenges that people face when they have to construct these buildings, and how they are helping the building occupants to be comfortable, just thermally comfortable without having so much energy use. So this is a great initiative. Thank you so much for Lilian Garcia for organizing this webinar. And yes, we have different webinars that are going to come in this series of webinars of focused green solutions. The next one is going to be about cyclones and storms. So if you want to register, don't hesitate to take this QR code. Thank you so much for the presence of everybody. I know it's 1 hour, but 1 hour to share very insightful results. So thank you for all the presenters of today as well.